listening to what should be a very educational experience today. My name is David Michael. I teach science here at Red Bluff High School. I teach some chemistry and some earth science classes. And along with that, I'm very, very fortunate to have been involved with this astrobiology program that we have here at Red Bluff High School. We have some students, you kind of see them up here and they'll introduce themselves. Many of you know some, or if not all of them, and you'll get to know all of them a little bit better by the end of tonight. But I'm very fortunate that I get to work closely with these students as a part of this NASA, Lassen and Volcanic National Park, Red Bluff High School astrobiology program. This is about the 5th year of this program in its current form, where we have these students that work really, really closely with these NASA scientists. The educational experience our students at Red Bluff get through this, it's amazing. It truly is a one-in-a-kind program. There's no other high school that's able and is fortunate enough to have a program like this anywhere in the United States. So we're extremely lucky and extremely proud of this program. As a teacher here, many times students ask me this, parents ask me this, talking about what I'm teaching, going, when are we ever going to use this again? When are we ever going to use this in the real world? Well, the great thing about this program is these students are taking the skills that they're taught here at Red Bluff High School, and they are using it to conduct research at the Lassen Volcanic National Park. And in doing that, they're helping us to better understand the park and helping NASA to hopefully better understand not just the park, but hopefully Earth a little bit more, and maybe even life or areas beyond Earth, meaning other planets and things like that. So it's a truly valuable, very unique program, and we are extremely proud of this. I'm going to introduce to you right now Ranger Steve Zachary. He's the educational specialist at Lassen Volcanic National Park. We've been working closely with him throughout this program. It's only through all his time and energy and effort that we really are able to go up there. And he's going to explain a little bit about the park's perspective and their involvement in the program.
Thanks. This is a special opportunity to have a partnership with NASA and Red Bluff High School. And actually, back in 2007, there was a get-together in the Bay Area of NASA and the National Park Service saying, how can we work closer together, do more education outreach, and involve students in programs that involve the National Park Service and NASA. So, Lassen was just this perfect site, with the mission to Mars and some of the things going on. Our park, with its hydrothermal areas and its volcanic features, was a perfect match for a program of this type. And so we began the ball rolling in bringing Red Bluff High School students, working with NASA and Lassen Volcanic National Park in developing a program that has been very successful over the years. And of course we have some of the top students, which I'm so happy to work with, and students that also have been involved in the summer interpretive intern program. That's where this kind of seed sprouted. Was we have a summer interpretive intern program for high school students. But this is going to be the 19th summer of bringing high school students up to Lassen, where they can interact with park staff, scientists, researchers, and others in working in the park. So again, it was been a perfect fit for a program of this type. And then with NASA Ames Research Center down in the Bay Area, everything just kind of came together, and we worked hard over the years to improve and make this program the program it is, a stellar program for students that many high schools all over the United States are very envious of. I get calls all the time, well, why can't our high school be involved in this? Why can't ours? Even some of the ones around Chico, Redding, and in North State, wondering why can't they be involved in this program. And unfortunately, we just can't take on every high school in the United States. And we'd like to somehow maybe mimic this and do something that other high schools could be involved in. At this time, of course, we can't. So it's just a pleasure to work with these students. They're so fun to be with, and it's just, you know, for me, people go, oh, working with high school students, that must be difficult. I go, no, it isn't. It's great. You know, I feel very lucky. You know, it's harder working with older adults than it is with high school students, I'll tell you. So it's just been a joy for me and a pleasure to work in partnership with Red Bluff High and NASA and the Park Service in this program. Okay, so I'll turn it over to Dr. David Des Marais. You want to say anything more? Sure, go ahead.
The teacher I never miss an opportunity to talk, right? That's all we do as teachers. Anyway, Dr. David Des Marais is going to speak a little bit now about Lassen and connecting Lassen to Mars, and then also some of the research that we've been doing up there a little bit. Dr. Des Marais is really our lead contact astrobiologist from down in NASA Ames. The Ames Research Center, for many of you, if you know this, it's down near Mountain View, about 3.5, 4 hours from here. It's a very convenient setting for us to be that close to it, and we're very fortunate. Without them as being close to us as they are, and as close to Lassen as we are, we would not be able to have this program. And Dr. Des Marais has the coolest title, I think, of any space scientist. Can you beat that? That's pretty cool title. So, Dr. Des Marais, go.
Thank you. To make some comments up front, one is, of course, a major motivation in NASA now is to engage the next generation in science and technology, even if they don't go into those careers, to have an appreciation of them. So we view that as one of our key roles. So that's the connection to education. And frankly, also, by being engaged in these activities, we're learning better how to communicate with people in the lay public, you know, high school students and everyone else. And it is, after all, the public space program. And certainly with our websites and the active involvement that people have shown in our rover exploration of Mars, you know, we try to continue to maintain and improve that kind of connection to the people who pay for this program. But also, more on a science note, the idea of exploring for evidence of life beyond the Earth really requires exploring for environments that we think would be most conducive to support life. And this has turned out to be a very important scientific approach, because if you're looking at a second object like Mars, you really need to have to understand this object as a system. You know, it's got a geologic activity, it's got a climate, it's got all kinds of aspects to it. And really, it's all those aspects that feed into whether or not that planet ever could have supported life. So when we make hardcore funding decisions about how much to put into geologic work or climate work or whatever, we strive to maintain a balance of funding so that we really are addressing the system effectively to understand that planet. And that also just happens to be the way to do it, to search for evidence of life. So in a way, there's science benefit beyond just searching for life, and that is having the most holistic, balanced approach to planetary exploration. And so a lot of what I'll say tonight is really in that spirit, and that is that, of course, now we are an amazing generation. We are the first generation to really be able to explore another planet in incredible detail, which, of course, our orbiters and landers really have done. And I think the public's interest in the stories that unfolds literally day to day on the surface of Mars is an example of that kind of real opportunity that people are taking advantage of. So I'd like to start the puzzle here with talking about what we have known about Mars for a little while. And of course, that's from the Viking mission, which landed in 1976. And the real focus of that mission was to search for evidence of life at the surface of Mars. And just to make the story quick here, we found that that surface environment was really hostile, okay? And it wasn't just because it was cold, but also because of the thin atmosphere making a very harsh radiation environment. And of course, a lot of radiation, a little bit is good, you know, sunlight makes plants grow, but too much is a bad thing. And there was plenty of that on the surface of Mars, but probably the most killing part about the surface of Mars environment today is it's just so dry. And it's so dry that it's literally orders of magnitude too dry to support life as we know it. And so this observation made by the surface landers of Mars really threw some damper on our thought that we were going to be able to go and see evidence of life there. But at the same time those landers were making those observations, the orbiters were making another really profound observation, and that is this evidence of huge stream channels flowing across the surface of Mars. This is actually in the northern lowlands here and the southern highlands coming off this way, indicating that huge amounts of water once flowed across the surface of Mars, probably very long ago, because a lot of these things are punctuated with craters. It indicates that a lot of time has passed since those channels were formed. And so the key point here is that that can't happen on Mars today. It's too dry. The conditions would not allow rivers of this type to develop. And some places you see where water erupted from the subsurface and then flowed out to the northern lowlands. So there was evidence of a climate that's just not like what we see on Mars today. And of course the key point is that planets can change profoundly over time. And this now gets to a broader theme in planetary sciences that NASA has been exploring. And that is, how is it that planets change over time, and what consequences does that have for the surface environment? And to start, Earth really provides a nice example of how planets can change so dramatically. But to just give you a perspective on this, think about the environment in which we live our everyday lives. And that is sitting on the surface of the Earth with an atmosphere overhead that allows us to have liquid water at the surface and all the amenities that are required for life to flourish. But the amazing fact is how thin that veneer is compared to the size of the planet. For example, think of some place from where we are that's 13 miles away, and just how far that is, how long you have to drive to get there. If you took that 13 miles and went straight up into the atmosphere, you'd be already about 80 to 90% of the entire mass of our atmosphere. And so even though you think you've got this big atmosphere up there, it's really incredibly thin compared to the size of the planet. And the key point is that because that's so thin, the processes that are occurring beneath our feet and coming in from space, above our heads basically, have really been very important for shaping the nature of this environment that we live in. So we live in a very thin skin on the surface of the Earth, and the point is that it doesn't take all that much change, either from above or below, to change the environment that we live in. Now, the other interesting perspective, and this occurred to me just to give an example, is we think of the Earth's crust as a nice, solid, deep, sort of solid foundation that we live on. But if you look at the crust of the Earth compared to the interior, the mantle and the core, it's analogous to the skin on an apple. And that is the skin of an apple divided by the radius of that apple is actually, it's almost the same, or in some cases thicker, than the entire thickness of the crust, which is like 20, 30, 40 miles thick, compared to the radius of the Earth. A very small ratio here, analogous to the ratio of the thickness of the skin of an apple to the interior of that apple. And the key point is that what happens inside that apple, or in this case what happens inside the Earth, is really been very important for helping us understand the history of climate on the Earth. And just to get to the point as to what a key process that's involved is the presence of radioactive elements that are distributed within the interior of the Earth. And because when they decay, they give off heat, and because the Earth is such a lousy conductor of heat, the interior of the Earth has gotten very hot. In fact, you know, you go several tens of miles beneath our feet, and it's so hot that you really can't survive there. And this great amount of heat inside the Earth eventually has to get out. And, you know, it just builds up and builds up until eventually it's coming out at about the rate that it's being generated. And I just want to make a point that these large temperature gradients, hot down there and cool up here, can be very useful sources of energy. We have geothermal well systems in California that produce like 5% of the energy in California. And just by tapping into steam that's down deeper where it's hot, we can generate megawatts of energy. And we've gotten some tricks in our quiver lately where we can isolate some of these radioactive elements. We can play some tricks by making neutrons to speed up these reactions, and we can generate nuclear power. So the interesting thing is that nuclear energy not only supports power plants of various types, but it's also the engine that drives so much of what has changed Earth over time. And literally, when you look at the map of the Earth here, you're familiar with the continents and, of course, the vast oceans. But underneath all of those oceans is a huge volcanic province. All of that is due to volcanic activity of this heat trying to get out from the interior of the Earth. And in the process of doing it, it literally roils the crust of the Earth, just like a boiling pot of water roils the surface of that water. as it's convecting and bringing that heat out from the interior of the Earth. And you think, well, that's down in the ocean, sort of in the way under the water. Why should I be concerned about that? Well, if you go back just a few tens of millions of years, 94 millions of years ago, all of our continents were a lot closer together. Why? Because they're being moved around on these plates of the crust that are a consequence of that heat coming out from the interior of the Earth. In fact, out here in the middle of the Pacific Ocean at that time, all the plates of the crust were moving apart, and there was so much heat coming out at this point that the seafloor rose to the surface, and we had an enormous Yellowstone National Park out in the middle of the Pacific Ocean just some 90 million years ago. Just 90 million years ago, the surface of our geography, surface geography of the Earth looked that different. And that's because of this heat generated by radioactivity and coming out on the surface. So the point is that these processes in the planet itself have a profound effect on the configuration, the geography of our world, and also in the composition of the atmosphere, as it turns out. And so there have been big changes in the system that we live in over billions of years here, where if we now literally go back billions of years, we actually have to take into account, as planetary scientists, that the sun's luminosity has changed substantially over time. That also in the early days, the number and size of impacts of meteorites was much greater than it was before. This has clearly had consequences for our surface environment. And getting back to the radioactivity, not only does the radioactivity provide this heat, but as you know, radioisotopes decay over time. And so the amount of heat that has been produced inside the Earth has actually been declining for a very long period of time. And if you look at that in reverse, you think, wow, there was a lot more heat coming out of the interior of the Earth back then. What consequences might that have had for the environment billions of years ago? Well, for one thing, you had CO2 coming out and water vapor and so forth. That clearly has an effect on climate. But of course, the other obvious thing is that back then, the volcanic activity on the early Earth was much greater than it is today, because you have a lot more heat trying to get out, and the most efficient way to get heat out from the inside of a planet is through volcanic activity. And so back then, volcanic gases provided greenhouse warming of the climate, probably much more so than the case today. And that's sort of a good thing, because I already told you that the sun wasn't as bright. And so in a way, the greater volcanic activity on the early Earth compensated for the less luminous sun. And of course, this has been a good thing for us, because the evidence has been that our oceans are more than 4 billion years old. And for that kind of a stable ocean, you need a climate system that can really bring things into balance. So the interesting thing is, what was the environment like back then? And of course, what might have been the prospects for life back then? How can we address that, given the antiquity of this period of time? Well, the interesting point is that there's a saying I just love, and that is that the future is already here. It's just unevenly distributed. I just love that. But I thought about that and said, well, we could say echoes of the past are still here. They're just unevenly distributed. Okay, unevenly distributed. What's that mean? Where can we go to get these echoes of the past, such as this volcanic activity? Well, you know the answer. A place like Lassen Volcanic National Park. If you go to places that have an anomalously high amount of volcanic activity today, compared to most places on the Earth, in a way, you're time traveling back to a period on the early Earth where processes and environments might be more like what life experienced in the early history of our Earth. And so the key to that understanding how the biosphere might have been like at that time is to get a sense of what the geologic processes are, the kinds of sedimentary deposits that are formed from them, what the climate might have been at that time, and of course what life might have been present at that time. And when all these things come together, we have what we call the biosphere, the space on the surface of the Earth where life can exist. But again, I already talked about a very important geologic process that plays a big role in this. And when all these things come together, you basically have a situation where you can have conditions that can sustain life. Well, what's that mean? It means that all the ingredients are present for life as it needs to have them, and it means that you have an environment that is stable enough and is amenable to support life. So you can think of it as being this cube here, where the boundaries of this cube are defined by several key parameters. The amount of water that's available for life, you need a solvent for life. The amount of ingredients that you have, the carbon, the phosphorus, the nitrogen, the kind of things that every farmer thinks about when they're trying to make their crops grow. And that has to be available, and you have to have an energy source. Okay, and of course sunlight being a great example of that. And so what was the availability and the nature of the conditions that would have supported life way back when? And we have this fascinating record of early life. This is like a geologic clock here where we start at the present, and if you dial back in time to the origin of the Earth at about 4.54 billion years ago, you don't have to go very far to where you begin to see evidence of life preserved within the fossil record. Very, very early in the history of the Earth. And the exciting thing about that is that there were no plants and animals back then. These are all microbial life, all the way around the clock until you get up younger than 1 billion years ago. Finally, we begin to see rudimentary evidence, and then finally very amazing evidence of life up to the present. The really robust, diverse, interesting life that we all come to know and love, plants and animals, are all younger than 543 million years in age. So basically, what was the nature of this early environment, and what can we infer about that? So that's an example then of how going to a place like Lassen could inform you about what that early environment might have been like, and therefore the kinds of organisms that could have existed. That said, let's go to Mars. We now have, as I said, this incredible opportunity to see a second example of a potentially habitable environment with the exciting prospect that potentially someday we might find evidence of life there. Well, some basic comparisons of Mars and the Earth are, that Mars is considerably smaller. It has less solar radiation. The gravity, because it's a smaller planet, is smaller than the Earth's and so forth. It takes longer to go around the sun. Interesting differences like that. The one thing that two things I really want to emphasize here, though, is that the composition of Mars is very similar to that of the Earth. So it should be hot on the inside. It should have those radioisotopes, just like I was talking about. And so in that sense, it's also similar to the early Earth, and therefore we would expect something like volcanism. But the other important thing I want to mention about Mars is it's smaller. And a smaller sphere, a smaller object, has a greater ratio of the surface area, which is the way the heat gets out, to the volume, which is where the heat's produced. And because of that greater surface to volume ratio on Mars, the smaller sphere, Mars, cools more quickly than the Earth, which means that the crust of Mars is colder than the Earth to a greater depth. That turns out to be a very important key to understanding some of the differences between Earth and Mars, because whereas the Earth has this amazing system of plate tectonics, as I talked about earlier, where the crust is moving around and the continents are on this perennial ride that just goes on, Mars has what we call a stagnant lid crust. The heat coming out of Mars was never enough to create plate tectonics. It's the so-called stagnant lid. We've had a single crust that's been cooler and more rigid than the Earth's, and so it's just going to be a different kind of geography than what we think of when we think of the Earth. But, like early Earth, early Mars had more volcanic activity because it had more of its radioactive elements early on, just like the Earth did. And so when we actually look at a Mercator projection of Mars here, where now this is north-south, and you're basically taking the surface of Mars and making a flat projection, we see evidence of enormous volcanoes that were very active in the past. Everywhere I got a white circle here, you see evidence of a lot of volcanic activity. And basically, much of the surface of Mars is what we call basalt rock, or lava rock, that at some point or the other flowed out onto the surface. And so, just like the Earth, Mars was much more active volcanically in the past. Well, this is sort of interesting. Maybe this will give us a clue as to how we could have had a different Mars early on that might have actually been able to support liquid water. And indeed, in just the last several years, we've now made a very comprehensive survey of much of the surface of Mars, particularly the southern highlands here. I should mention that the blue is northern lowlands here, and these are the southern highlands of Mars here. This is a big impact crater. But when we look at this in terms of where all these little lakes used to be, and all these little blue squiggles are actually channels where literally we had precipitation falling on the ground and water running off to form these stream channels. The key point is that there was pervasive evidence of precipitation on early Mars. And we know it's early Mars because a lot of these little features are missing, right, where these huge volcanic eruptions have covered over these rivers and valleys, such that these must be older than 3 billion years, 3.5 billion years in age. So that early environment of Mars really was really different. It was certainly wetter than it is today, and perhaps it was also somewhat warmer. So when you tell this to an artist, they immediately say, well, what did it look like? Well, I mean, this is an artist's representation of what early Mars might have looked like if you take the water that we know is there and put it up on the surface and let it flow into the lower parts of the geography, and that's the northern lowlands up in here, Valles Marineris, a huge canyon would be full of water. For all we know, perhaps it looked like that. Well, that's not been proven yet. But there are some things now that we can say when we compare early Earth and early Mars. They both had a lot of volcanic activity, which certainly would put a bunch of water and CO2 into the atmosphere, and that's probably where the nitrogen in the atmosphere came from. There was definitely evidence of standing water on the early Earth, and perhaps then surface water, as I already said, on early Mars. And just a number, and of course we both share the same sun, although as you can see here, the sun is a little dimmer when it's viewed from out at Mars. But there's a lot of similarities here, and the key question is that enough similarity to have the potential to have had habitable environments that could have supported life had it been there on early Mars? Well, again, analogs of Mars past are still around, but they're unequally distributed, and just like I said before, to understand this early Earth, early Mars scenario, a place like Lassen Volcanic National Park is really a great place to go, because the geologic processes that are there and the water activity that's there is very reminiscent, we believe, of the kinds of things that would have happened on early Mars. And the same little box I showed you earlier, where we then would want to know where you had enough water and nutrient availability and some source of energy, where all those things might be in the same place, would be a great place to go exploring. So we've gone to the surface now. It's just amazing when you look at this, how many of these landers we've put down now. These are the Viking landers from the 70s, Pathfinder from 1996, Opportunity and Spirit, we launched those in 2003, and then the Phoenix mission here, which came a little bit later, actually, yeah, right up there, 2005, to a very high latitude. And the idea then was to get down on the ground and actually do the exploration. This, of course, is the rover, it's either Spirit or Opportunity rover that we sent to see if we could actually find evidence that liquid water had been persistent back there, see actual chemical evidence, things that we can see with the rover, sort of like a robotic field geologist that we figured out to send to Mars. And where we went, one of the key places that we went that's really relevant to Lassen tonight is Gusev Crater, and this was something that Spirit rover actually did. Gusev is a crater about 180 meters across, 180 kilometers across, but the key thing about it is that there was this huge stream channel, Ma'adim Vallis, that flowed into Gusev Crater. Filled it up, this is one of those crater lakes that we had identified, and then eventually it overtopped and flowed out into the northern lowlands. We even have a volcano nearby for good measure. So we thought we would go there and actually see if we can see evidence for persistent standing water and make some assessment about the habitable conditions. This is a National Geographic Society artist's rendition of what this site might have looked like back then. There was the stream channel flowing into Gusev Crater and Polyneris patera blowing its top there in the background. Obviously an exciting place to go to. But when we landed up here in what we call the Columbia Memorial Station, this of course launch happening just a few years after the Columbia, we lost the Columbia space shuttle. It landed in a huge volcanic plains, basaltic plains. Well, we didn't go here to land on a bunch of lava rock. We wanted to look for a lake bed, but we saw these hills in the background, these Columbia Hills, again named after the Columbia mission, and decided to drive over there and explore this area. And this little artist rendition, we plopped a rover here in the middle of the landscape that we photographed as we climbed up into the Columbia Hills. But the real target of our exploration turned out to be an area called Inner Basin. So we drove up here, up Desmond Hill, came down, went into Inner Basin, and this key feature, home plate, is really what is the connection to the rest of the talk. We decided that that was such an interesting looking feature that we needed to go there. Well, when we get there, of course, just to remind you, Mars is a very dry, dusty, cold place, and that didn't change when we came over here, but this interesting feature of home plate, which I sort of indicated right here, was really what caught our attention. And what we found was that this was formed by, as an outcome of a violent volcanic eruption, that we throw a bunch of ash and everything up into the atmosphere, all kinds of material thrown up, and when it comes back down, it forms what we call a base surge deposit, and then also it forms, all this ash settles down, the wind blows it around, and you get the features that we see here. So we clearly found an area where there was a violent sort of volcanic eruption, and just because the students went to a place like that yesterday, and play a little video here which reminds you of what these are like. So this is an overflight of Hawaii, East Rift Zone, showing sort of the fountaining and everything we found evidence for at that crater, at that location. And this is a feature that's similar to what the students actually went to yesterday in their last field trip of the year. But I want to point your attention to these gases, sulfur gases coming out, water vapor coming out, very important aspects, and CO2 also, very important aspects of a volcanic eruption. And these are the kinds of processes that contribute gases to support the atmosphere and also create the terrain and features that we see. And when we look more closely at this home plate feature, which is about 90 meters across and a couple meters tall, we saw deposits that were evidence that liquid water had interacted dramatically with this eruption as it was happening, creating salts of sulfur, that very soluble salts being deposited because of the sulfur gases oxidizing and interacting with the rock and breaking it down. And also other deposits of silica, which reflect the rock being dissolved into this very hot water, dissolving the silica, and then as the water evaporates or cools, the silica forms deposits, much like you would see around a geyser, like in Yellowstone National Park or in some of the areas in Lassen Volcanic Park. So we were really excited about this. My gosh, here's evidence of a not only volcanic activity, but water interacting with volcanism. And just to show you, of course, how dramatic that can be, Iceland, it's hard to beat Iceland when it comes to amazing water features. And here's one. So this is what we call a drowned geyser, where water just filled up the geyser, and every once in a while the pressure builds up, the temperature builds up enough to explode up into the atmosphere. But just point your attention to all these deposits that are around the perimeter of this geyser, and they're very interesting because this is an environment that satisfies all these requirements. We've got the availability of liquid water, we have the stuff that is dissolved in the water that could be nutrients for life, and just the sulfur gases alone within these eruptions could be a potential source of energy for life. So this is a very exciting place, and we'd sure like to see if and wherever there could be good places on Mars. So here's sort of a history then of Mars from the past up to the present, where we see an ancient surface environment with lakes and streams and much more active volcanoes. But over time, as the interior cooled and the atmosphere deteriorated, we descended into the very cold conditions that we see on the surface of Mars today. But this is sort of to illustrate, shown in blue here, environments where life could potentially have been supported on Mars, and that's what the blue area represents. Today, you'd have to go 2 miles or so into the subsurface to find stable liquid water. The green here represents, however, deposits that used to be in this happy zone back here, but are now very dry and no longer could support life, but they might contain within them some kind of a record of what that environment was like and what might have been living there. So the question is, how do we interpret those things? If we can go to a place, like indicated by these little green craters here, where this material is available, how do we learn how to interpret that? Recognizing that just like I showed you before, you have these key elements of a biosphere, the geologic process, the climate, and the life. On Mars, we don't know about this part of it. All we know are the processes that happen, and we have deposits that might remember what that was like billions of years ago. But how do we learn how to interpret those deposits if we don't really have the luxury of actually seeing the life or actually measuring the climate? Well, again, these hydrothermal sites on Mars are really potentially great places to search for life, because it seems that when we look at the Earth, they provide all the ingredients that you need for life. We think we may have found an example of this now at Gusev Crater, as I explained with home plate, but Warner Valley in Lassen Volcanic National Park is a pretty darn good analogy to what might have been the case in this inner basin here and at home plate billions of years ago. And some of these field sites that are shown on this map will be explained by the students. And we'll explore the hypothesis here, and that is that oases, these are great places because they're sources of near-surface water, that they produce, have reduced chemical species. It could be a source of energy for life. Mineral deposits, it could preserve evidence. Those are the deposits that are from that feature that could potentially remember what their early history was, and that perhaps there's a variety of biota there, and therefore these ancient spring deposits might have been great places to search for life on Mars. And so by going to Lassen, perhaps, in Warner Valley specifically, we have the ability to study all those circles. And we have the ability to understand the kind of biosphere, at least locally, that could have been produced there, as evidenced by what we might see at Warner Valley. And therefore, by analogy, it would inform us as to how we might search for evidence of life on Mars. So to sort of finish up here, Earth and Mars are very similar in many respects, and they even were more similar in the past, okay, in the sense of liquid water being at the surface. Rocky planets, geologic processes, volcanism, these are things shared by Earth, Mars, and other rocky planets that might exist beyond the Earth. Water activity was definitely much more the case on Mars in the past. The question is there any of it today, maybe in the deep subsurface? The Spirit rover found an ancient hydrothermal system on Mars. Volcanic activity interacting with water, we think it could well indicate that it was a habitable environment. But how can we analyze the deposits there to really be sure? How do we learn how to do that? How do we interpret the record in these Martian deposits? Well, the answer is you go to similar environments on the Earth, such as at Lassen, to really try to figure out the key to the lock that will unlock this mystery of what the early habitable environments on Mars might have been like, and whether life ever lived there. So with that, I'm finished with sort of the intro, and perhaps we should just stop there. Or should
You have 5.
do we have 5 more minutes?
You did.
Well, I could say a few things about Curiosity rover. Okay. Well, my disclaimer at the front end is we haven't found evidence of hot springs or anything at the Gale Crater site where Curiosity landed a year and a half ago. But it's been a very exciting trip so far, and I'll just try to show you some pictures quickly. First of all, this rover, Curiosity, is a much more capable rover than Spirit and Opportunity, where it literally carries a laboratory with it that can do mineral identification of gases and organic matter if it's there. Gale Crater sits right near the equator, between the southern highlands and the northern lowlands. It's very deep. The deeper you are and the closer you are to the equator, the better chance you might have had liquid water being persistent in the past. But what really made the deal for us was this crater used to be completely filled with sediments more than 3 billion years ago. And then these sediments got exhumed in some mysterious way, but there's still this mountain in the middle, which has, we think, within it, a record of hundreds of millions of years of history of Gusev crater between 3.8 and about 3.3 billion years ago. A virtual gold mine to understand what could have happened on Mars at that time when there was still liquid water, but it was beginning to go away. Here's where we landed. We want to go to that mountain, but you have to land in a nice flat place where it's safe. Well, we thought the flat place was going to be boring, but at least we're close to the mountain, we can drive over there. Well, when we studied Gale Crater more closely, we found shoreline features. In other words, not only do we have this mountain in the middle with a wonderful record of early environments, but even after most of the sediments were removed, there were lakes forming within Gale Crater, and darn it, we didn't land in a place that probably was underwater at some point. So when we landed, we decided to drive over to a place where we thought some very interesting rock deposits were being exposed. And this is sort of a warm-up plat before we started heading towards the southwest, towards the mountain itself. So we went into this Yellowknife Bay, and we saw some deposits that were just very exciting to us. They almost looked like mud cracks, and here's places where cracks were filled with some kind of mineral deposit. So we were very excited about maybe even making some kinds of discoveries here. So here's our arm going out, we're drilling a hole there, and when we drilled the hole, we got this beautiful gray material coming up. And I say beautiful because it's gray, meaning it hasn't been oxidized by all that radiation. And so we don't have to drill very far into a sediment to get really pristine kind of stuff. So we got very excited about that when we did the X-ray analysis, and I won't explain how you read these things, but we found an indication in the drill core from this lake bed place of clay minerals that require liquid water for their formation. Okay, so now we have mineralogic evidence that water really was there, this probably really was a lake bed, and it persisted long enough for these clay minerals to form. Very exciting. And then when we heated up the samples, we get water out, we get carbon dioxide, sulfur gases, we see all the kinds of building blocks that are essential for life being locked into this rock. In other words, by all accounts, this rock was from a potentially habitable environment. All of this before we even got to the main event, which is the big mountain. And by the way, that little tiny dot is how big the rover would be in this picture, the little tiny dot that you see there. So this is an enormous deposit, and of course this is now where, as we speak, we are driving. And just to make an analogy here, if you've ever been to the Grand Canyon and you look at all these incredible layers that speak to hundreds of millions of years of history, that's analogous to what we're driving towards in Gale Crater. In fact, this thing goes up for another, 2 miles above here, a huge record of early Martian history that we're heading for, and that's really the main event for the mission. Along the way, we're at a place called the Kimberley, and this picture is actually on it's on your announcement for tonight. This is where the rover is right now, okay, as we speak. And what are we doing here? Well, we got down here and we drove around to a ledge that's part of this deposit here, and we're going to do another drill hole. And just to give you some exciting, this happened a week ago. If I can find my little pointer here. There we go. And now, so here's the arm. Here's the drill right there. It's poised above the surface. So watch that when I start the movie. And also, this is a little sandy area. Watch that. We actually, it's amazing. We're 200 million miles away and we're doing home movies. There we are. This is, okay. So then watch the drill go down, and then you see it's shaking the ground, and then you're getting a collapse there. So that's actual little sequence of pictures that were taken about a week ago on the surface of Mars. Here's another one, which shows the, it's sort of like trying to comb your hair with a mirror or something. Here we go. That's before, after. That's the drill hole. That's the short drill hole. Today, as we sit here, we are drilling the big drill hole, which will actually be where we get the samples. Anyway, you can see evidence here of also a lot of shaking going on. So we are, as we speak, continuing to explore the record of Mars, but we still need to do the kind of work on the Earth to help us interpret these sediments and these deposits that we're going to see. And that's really where the students' project and our work at Lassen comes in. So thank you very much. Take selfies. This is a self-portrait taken by everybody else. And with that, we're finished. Thank you.
I know.
Thank you very much. I'm sure many of you have some questions. We're going to wait till the very end, though, so if you have questions, just hold on to them. We'll let you ask them right at the very end. Next up, we're going to have our students talk a little bit about all the work that they've done this year. Now, a little bit about the program from their perspective, the school's perspective. All these students have completed chemistry basically to be eligible to participate in this program. Our requirement is that you have to have finished chemistry because that then gives you the scientific background to really understand and dig deep into this project. So because of that, all these students are at least in their junior year of high school. We have some juniors, we have 5 seniors as well. There are 4 students that are in their second year of this program. So they began their junior year and now they're wrapping it up at the end of their senior year. This program really takes on a life of its own, and it's something that as they get into, I don't know if they're really aware of how much work they're doing, because I know that they really enjoy what they're doing, but still it takes a lot of time. We meet most every Monday, at least 2 to 3 Mondays a month. That's done after school. The project and the commitment that they take then requires them to do work on their own a lot of times. And basically what this is another class that they're taking here at Red Bluff that they're not receiving a grade for, that's taking time away from their studies in their other classes. And so you can see the tremendous amount of commitment they just have to have for this program. All of these students have done a great job balancing that with all their other responsibilities throughout the course of this year. Many of these students are currently taking AP tests this week and next week. They're involved with sports, countless other clubs. They've gone to Austria. Who went to Austria? Shelby.
I went to Austria last year.
Did someone go to Italy too this year? We've been everywhere. And so they're involved with a lot of things. This is just one more thing that they're involved with. And so the reason why I'm sharing all this with you is I just want you to appreciate how hard they've worked this year. So as you sit back and just kind of listen to what they talk about and have them explain to you all that they've done this year, just kind of appreciate from their perspective all the work that they've done. So, ready? Got a nice blue screen for you. Is this good for you? That's the top. Okay.
There we go. You gotta shake the mouse.
Hello everyone. On behalf of all the interns, I would like to thank you for attending the Lassen NASA Astrobiology Internship Program presentation. Throughout the past year, we've all been asked the standard, "What's that NASA thing you're in?" question. So we're excited to finally explain what we've been up to this past year in greater detail. We'd like to start by introducing ourselves. My name is Mason Trujillo, and I am the Senior Head Coordinator of the program.
My name is Brandon Luco, and I am a senior.
My name is Jessica Trell, and I'm a junior.
My name is Molly Shea, and I'm a junior.
My name is Julian Strom, and I'm a junior.
My name is Marissa Chase, and I'm the senior leader for the house.
My name is Lily Fryer, and I'm the senior advisor for the Nuclear Group.
My name is Socio Sullivan, and I'm a junior.
Hi, my name is Adrienne Stager, and I'm the senior leader of the Alpha Group.
Hi, my name is Farron Spangler, and I'm a junior.
Hi, my name is Natalie Renfro, and I'm a junior also.
So the formal definition of this program is that it's a partnership between Lassen Volcanic National Park and NASA Ames Research Center, in which we, the interns, conduct research regarding the Lassen's climate. However, I think throughout the presentation you'll learn it's much more than that. Throughout the presentation we'll discuss field trips, what is astrobiology, why Lassen, what is habitability, field work in Lassen, experiments/explanations, and overall connection to Mars.
So during the course of the program, we were fortunate to go on many field trips, and one we went on was the Ames. We went to the Ames Research Center, which is located near Santa Clara. And while we were there, we were able to visit and walk in the largest wind tunnel in the world, which you can see in the bottom right corner. And we also went to a laboratory where there was a 3D printer, which we all got to test and see firsthand. And we also went to another laboratory where they were doing science experiments where they were seeing how plants would grow and interact, and they were sending them into the International Space Station and seeing how they would survive. We also went on another field trip to Sulphur Works, which is also a field site in Lassen National Park, and we snowshoed while we were there. And we hiked to our field site where we took field samples and also conducted lab research while we were there.
Yesterday, we were fortunate enough to hike Cinder Cone. It was about a 1.2-mile round trip hike. It was really fun. It just allowed us to see a different part of the park and a different type of volcano. So now kind of getting into our work. This is Warner Valley. We originally went here at the beginning of the year to collect most of our samples. This kind of shows an overview of Warner Valley. On that circle on the top part of it, that's where the alkaline field site is where we sampled, and then on the lower part is the neutral field site. And then over on the other side we have Devil's Kitchen, which was our acidic site. And right through Devil's Kitchen is a fault line that allows for the volcanic gas to come through. As I was just saying, at the beginning of the year, we went to Warner Valley. It was an overnight camping trip. We collected samples for both the rock dissolution experiment and the micropulturing experiment. And we did lectures at night, and it was so much fun.
Okay, so Dave just talked to you about kind of like why Lassen and what astrobiology is and how it relates to Mars. But in the context of this program, maybe wondering why do you go to Lassen so much and what are you doing there? Well, the reason that we sample at Lassen Volcanic National Park is because it's a unique and it has a range of conditions such as like pH, conductivity, temperatures that can support life. So we want to, basically, we're researching the range of conditions that can support life, and Lassen provides all of those. And then also, what is astrobiology? So the formal definition of astrobiology is that it is the investigation of the origins, distribution, and future of life in the universe. And our research is important in identifying the range of environments microbes survive in, so the search for life in the universe can be directed to planets and specific regions on those planets. So he talked to you about the Gusev crater, which could have supported life. So our research is important in directing the search towards those regions.
So we're all here because we go through our daily human functions of eating, sleeping, drinking, and as a result of that, we all grow, whether it's vertically or horizontally. And microbes are basically the same. If they have a solvent, they have their raw materials, their food, light, energy, and favorable conditions, they're going to grow. So what we look for is an area that has all these four, let's say, situations. And you can see by in the middle, like where they all cross, that it's very hard to find an area with all these situations in it. So that's why we do go to Lassen, because it has these habitable environments for the microbes that we are looking for.
So here's a diagram about the water pathways in Lassen Park. And all the water starts out with snow and rain. And some runs off and some soaks into the ground. And when it soaks into the ground, the magma heats it up. And when the magma heats it up, it comes into sulfur, which it rises up and turns acidic. And so we've been in this split into three groups: the acid group, the alkaline group, and the neutral group. And these are pictures of the neutral group at Paddle Wheel Creek. And you can see like the lush grasses, and there's nothing dry because it's the neutral. And the water pathways of Devil Kitchen and acid it goes straight up from the ground, so it's the most acidic. And then the alkaline vents, the water comes up and interacts with rocks, so it slowly comes up. And then Paddle Wheel Creek and Rapids in the neutral water, it's runoff water, so it's neutral and it's not so acidic. And here are some pictures to describe the environments of each site. This one is the neutral, so like I said, it's very lush, it's very green. This one is the alkaline site, it's very rocky where the water interacts. And the two top pictures are the acid sites, so it's very dry. Involves sulfur.
For the field trips, how we conducted our methods of getting all of the samples together was through using a pH and conductivity meter and collecting rock samples and microbial samples. The materials, pH, conductivity meter, sample bottles, syringes, and a laser thermometer. How we collected the samples, we were all gloved up, wearing protective eyewear, long sleeves, especially if we were taking samples from the acidic site. And we used a syringe and a filter and put the samples into sample bottles. And then that night on the overnight trip for the first experiment and for the first real field trip that we had, we cultured them when we went back to camp.
So you've heard us say several major terms for the kinds of measurements that we've taken. So we took our conductivity, obviously, with a conductivity meter. And conductivity is the concentration of ions within a solution. And the importance of that is that the more ions that are present in the solution give us evidence to believe that the water has interacted more often with the rocks that is underneath the water. And the second major measurement that we have taken was with pH. And pH is a number that measures the overall acidity or alkalinity of a solution based off of the number of hydrogen ions within the solution. So to give you a little bit of perspective, lemon juice is very acidic, has very high concentration of hydrogen ions, and it has a pH of 2. And bleach is very basic with a pH of 13 and a low concentration of hydrogen ions.
So we had two major experiments, and one was a rock dissolution lab where we were trying to mimic what was happening with the water and the rocks in the environment. We had the microbe culturing experiment where we were trying to rebuild the life of the microbes from the environments that we took them from. And our goals were to just mimic the key processes at the environment. And then for the rock dissolution experiment, we took some of the rocks that we thought were at each field site, and we put them in an acidic solution, and we were seeing whether or not the cations and anions would come out, because the cations and anions were the sources of energy for the chemotrophs or any of the microbes.
So we had different instruments and we had a set of titrations for the experiment. The instruments for this were the pH and conductivity meter, which we used in the field. The setup was we powderized the salt and andesite and put that into plastic containers. And when we put that plastic container on a hot plate, and then the initial pH of the salt and andesite was 3. So when we titrated it, titrating is neutralizing the change of pH. So we titrated once a week we would titrate each of the salt and andesite, and then if it was more acidic or alkaline, then so we would add sulfuric acid to make it pH of 3.
So, hypothesis 1 of the rock dissolution experiment. Interactions between water and the andesite and basalt rocks in Warner Valley are reflected in the concentrations of metal cations in the field water samples. So basically, we know that water dissolves rocks. So by identifying the elements in the water, we're able to figure out what the composition of the rock was. And this graph represents our hypothesis. The y-axis represents the abundance of each element in the rock, and the x-axis represents the abundance of each element in the solution. This shows the most significant element is the most significant element in both the solution and the rock, creating a 1-to-1 ratio, or a trend at about a 45-degree angle.
Our second hypothesis for the rock dissolution experiment was that the differences in the elemental makeup of our two rocks we tested, so basalt and andesite, the differences between them would create differences in the metal cation concentration, or the elemental makeup, observed in the field and lab samples of the water that had interacted with the rocks. So in this graph, the percent composition of elements in the basalt sample collected from the field is plotted on the y-axis, so over there. And the percent composition of andesite in percent composition of elements in the andesite rock collected from the field is on the x. So the graph shows that the relative amount of these elements in each sample are present in a 1-to-1 ratio as compared to each other. So like Mason said earlier, 1-to-1 ratio creates a 45-degree angle line. So the elements are present in the rock in virtually the same amount relative to each other. This means that our second hypothesis cannot be proven or disproven because it is based on the assumption that they are the same, which clearly they are not. So since the first half of that hypothesis isn't true, the second half can't be determined. We can't make an assumption based on something that isn't true.
Okay, so our third hypothesis was basically trying to prove that when water and rock interact, the pH is somehow affected. So what we tried to do, we took what we saw in the environment and tried to replicate that in a very simplified way. So what we did was, it's the rock dissolution experiment, so what we did was we took andesite and basalt rock and exposed it to sulfuric acid at a very high temperature. And so as a result, the rock buffered the solution, increasing the pH and making it an alkaline environment. So that ultimately proves that when rock and water interact, it affects the pH. So this graph kind of represents our experiment. On the x-axis we have time, and on the y-axis we have the amount of acid that we use to titrate our solutions back down to 3. And so as you can see, as more time passed by, we had to add a certain amount of acid. And at first, it required a lot of acid to titrate our solution, and that was simply because the smaller pieces of rock were dissolved first and immediately affected our solution at a faster rate. And then later on, we were left with the bigger chunks of rock, and so it didn't affect our, it didn't increase the pH right away, so we didn't need as much acid.
And so our fourth and final hypothesis for the rock dissolution experiment were that solutes derived from volcanic gases strongly affect the pH and the concentrations of the other solutes at the different field sites. So all the water that we see in Lassen Volcanic National Park comes from snowfall, and the snowfall then melts and is either runoff, which then goes down the mountain, or it seeps through the rock beds and then goes down to the center, or it's heated up by magma and it rises as sulfuric gas. And so at the Devil's Kitchen, which was our acidic site, there was a constant, steady flow of the sulfuric acid rising at a rapid ascent. And since it was constantly going, it didn't have time to make a strong interaction with the rocks, and it also wasn't able to dissolve along with the salt rock, which creates alkaline conditions. So as you see on the left, at Devil's Kitchen, the condensed water at the top we found was extremely acidic, which we also proved in our experiment. Whereas at the alkaline spring, there's also a rise of sulfuric acid as it grows, it condensed with water and also interacted with the basalt rock, which created it more alkaline. So then the water that we saw at the surface was measured with the pH meter to be more basic. And overall, this is what our experiment proved with an alkaline site and proved how an alkaline site becomes alkaline.
So for the microculturing experiment, we were trying to see if we could grow phototrophs or chemotrophs, depending on what we thought we had in the field. And that was mainly based on the color of the microbes that we saw. And we gave them a sulfate compound for some type of energy source, and then we incubated them, and we waited for them to grow, and then after they grew, we took pictures of them underneath the light microscope.
Our hypothesis for the microculturing experiment was the acid-neutral alkaline sites create, the acid-neutral and alkaline sites create a range of environmental conditions. We tried to test this by trying to replicate the environmental conditions that we saw in the field at our sites. Here, environmental condition refers to the pH, the chemistry of the water, and the temperature. The chemistry of the water is referring to the materials in the water, the ions, nutrients that help microbes grow. For the lab, so we collected our samples all from our respective field sites, each group with their own field site. We used giant tweezers to lift the microbes out of the water and pipettes to get other materials out. When we got back to the campsite with our samples, we put them into test tubes which had growth media in them. And the growth media was made to affect the microbes like Miracle-Gro affects plants. But Miracle-Gro is specialized for different types of plants. And that was the case with the growth media as well. The acid group's growth media was more acidic, and the neutral group's media was more neutral. So
I missed introductions. I'm Shelly Bacala. I'm a junior and I was in the acid group. I'm going to talk to you about the results of our microbe lab. The neutral group had a more habitable site for microbes because it's neutral and less extreme temperatures. Whereas the acid and alkaline groups obviously had extreme pHs and higher temperatures, allowing less life to live there. Extremophiles, which are organisms that can live in extreme conditions, end up residing in the alkaline and acid group. The neutral group grew many phototrophs, which are organisms that use light to produce energy. And that's seen in the green colors in there. And then also they grew more of a variance of life with the different shapes between filaments and then the smaller microbes and that. And then the alkaline group grew phototrophs as well. But the life wasn't as diverse. As you can see, it's just like one big kind of filament, like bunch of filaments. And then in the acid group, we grew algae and phototroph, and then we also grew what we thought was like an ironized crust, but it was actually grew microbes as well, and white streamers, which are chemotrophs, which use chemicals to produce energy. Life was also less diverse in the acid group, but we did manage to grow some stuff.
So why Lassen? Well, one, it's in our backyard, so why not go to something that is so near, like versus going to Mars? And secondly, like David was saying earlier, there are evidence of hydrothermal areas, and those are at Lassen. So by studying them at Lassen, we can find where we want to go on Mars, where interesting sites can be on Mars, and instead of, taking a guess, throwing a dart, saying, oh, let's go here, we can actually map and locate where we can find interesting hydrothermal areas.
So as you can see, this past year we've learned a lot. However, scientific knowledge isn't the only thing we're taking away from this program. Like for me, one of the most important things that I've taken from this program is how to be a better leader, and this program has given me the skills to do so, which will hopefully help me next year when I attend the University of Notre Dame.
It's taught me how to run experiments, like actual experiments from field sites and in the lab.
It's taught me how to use stuff we learn in school in actual places.
It's taught me how much closer every planet is, how close to the relays they are.
The impact that being a member of this intern program has had on me is that it just gives you a reason to be really excited about science.
I've learned that no matter how much you study theory in class and read books and take notes, you can't really experience what it's like to do actual lab experiments that weren't written down for you and made up for you until you actually do it for yourself.
I've learned a lot of things in this program over the past 2 years, but I'm incredibly thankful for all of the experiences and memories on field trips and the labs and experiments and all the learning opportunities that were created based off this program.
I've enjoyed the experience because you're able to take directly what you've learned in the lab and then apply it to real world situations, and that's just different from any classroom setting that I've ever been in. And my plans after high school are to attend UCLA.
Hello again, Adrian, in case you forgot. It's easy, we're such a great group of people. Yeah, one of the biggest things that's made impact on me is being in a group of smart, talented, funny individuals and meeting scientists that actually work in a lab, they love what they do. Being around those type of people has really made an impact on me and has helped me decide what I want to do in the future that maybe research is right for me or being a scientist. And I plan on going to that was UC Berkeley, majoring in physics.
The overall impact that this program has had on me is just the great adult-youth partnership that is created through this program, that we get to work so closely with passionate people that care about us and that will actually actually phone us on the phone every Monday, or drive 4.5 hours to come sit with us, even if we're eating or accidentally nodding off or something like that. That they still love us.
This has impacted me by showing me that hard work truly pays off in the end. I mean, 2 days ago we were hiking up a 75% gradient that was sand, but it benefited us, and we're giving you this speech today, and it just shows like, our second hypothesis didn't work, but we're gonna keep going and search, and like keep researching the hydrothermal areas of Lassen.
So before this program, I didn't really know what I wanted to do in science. And I really like science, I really love it, and that's why I got involved in this program. But it has really opened many doors and opportunities for me for science and to really see what a vision of what I want to do.
And before we go, we wanted to take the time to thank all the mentors and scientists who have helped us for so long. And over the 2 years that I've been here, they've always been some people that you can easily go to for advice for anything. So we have these picture frames with our picture, and it's a group photo. And we're gonna give, so we can call them up. We can start with Mr. Michael and Mr. Nolan. And also Dave, and Nikki, and
So before the students get away, hang on. Before our interns get away. So this is the part of the program where we'd like to recognize their hard work with some awards. So I'm Mike Kubo. I'm from NASA Ames Research Center. I'm the lab manager there, and I've been a part of this program now for, this is our 6th year actually. And every year it gets better and better. We keep saying that. Every year the program gets better, it gets richer in content, and every year the students seem to get better and richer. And they bring so much to the program every year. And this year's group of students have been no exception to that rule. They've been really amazing, and it's been really fun to work with the seniors for the last 2 years, and to see them develop as both interns and as people, coming from just sort of students in the lab to leadership positions. It's been a real joy, and it's been really fun getting to know the juniors this year. Again, you start with these incoming juniors. They're about 16 years old, and just seeing them develop, developing their scientific instincts, seeing them develop how to learn how to work hard in the lab, learn how to take some responsibility over a project is a lot of fun. So we'd like to go ahead and start by recognizing everybody. We're going to start with the juniors. I hope organizing this way. Oh, actually, here, do you want to go ahead? Yeah. So I'll read them off. I'll give them to Steve, and he will give them their award. So the first person we'd like to recognize is Molly Shea. And if the students could pause for a quick photo, that'd be great. So the next person we'd like to recognize is Jillian Strong. Okay, next we'd like to recognize Natalie Renfro. Sure. Yeah, get your camera ready, Mom, because next is Mary Spangler. for you to keep and one is for you to give to mom and dad. So you can put it on the refrigerator.
Right in your portfolio.
Next, we'd like to recognize Brandon Lugo. Your hand. Brandon. Next, we have Jesse Cantrell. Next, we have Socio Sullivan. You can always rely on Soci for comedic relief, right? And I believe the last of the juniors is Shelby. Hey, Shelby!
Home run hitter.
And now that I found out that she plays softball, I'm definitely going to try to rope her into an internship at Ames at some point in the future. Okay, so now we're going to move on to the senior leaders. First, I'd like to recognize Marissa Chase.
Let me say something about Marissa and Lily also. They have been in the intern program for a couple of years as the astrobiology interns, but they also were in the summer interpretive intern program. So they've been in solid for at least 2 years every month. So it's been great having them.
Let's see, next we'd like to recognize Lily.
Lily.
Next we have Adrian Stager.
To the cinder coin and back.
Yeah, I made it.
She did.
That was
She did
tough.
a real job.
Nice job.
Yeah.
And of course, last but not least, we have Mason. And of course, we'd like to also recognize, the Ames group would like to recognize all the other participants other than the interns that make this program possible. And of course, by that we mean Mr. Fred Null and Mr. Dave Michael. We also gave you 2 copies, one for you, one for your parents. I'd just like to say a quick, really, we really appreciate these guys' hard work and time. This program takes a lot of effort, not just on our parts and Steve's part, but these guys put a lot of effort into making this program possible. So thank you guys very, very much.
Thank you.
And of course, Ranger Steve Zachary. And again, really makes the program possible. There's no way we could do this without him. He gives us all of our opportunities to get out in the field up at Lassen, and just a great guy. So, and we also really want to thank the families and friends that support these interns and make this program possible as well. And so thank you all. Thanks for being here. So with that, I think we're going to take some science questions and answers, or take some science questions from you, and we'll give you science answers back.
Or any questions that you might have for the interns.
So I'd like to welcome up Dr. Nikki Peranto, who's also part of the Ames team. Scientist in our branch, and I think her and Dave and the students are here to answer, and I guess me. Yep.
Yeah, absolutely.
At the time, Anyway, so if you guys have any questions, now's the time. Any questions for the students about their presentation, about their project? Yes.
Are we going to Castle Ramos for dinner again this year?
We'll get that part out of the way, yeah. So as soon as this is done, yeah, exactly. So as soon as we're done with this presentation, which will be not too long here, we very quickly need to reset up this room. Give us maybe 5 or 10 minutes to make that happen, and then we'll all, whoever wants to join us for dinner over Casa Ramos, you're welcome to join us.
When you go there, if you go there before the rest of us get here, the reservation is under Sandy NASA. And also I wanted to say, if there are any parents, friends, family who have comments that you've noticed about your kids being in the program, or you have anything to say about the program, we would appreciate those also.
Yeah. So any questions?
How many rovers are still operating?
2. Yeah, Opportunity and then of course Curiosity. Yeah, we lost Spirit about 2 years ago.
And just a quick note about that always impresses me, and Dave, correct me if I'm wrong, but we have had, the U.S. has had tremendous success landing rovers on Mars and landers on Mars. And I think the Russians have tried something like 25 or 26 times and never made it. They've had what we call hard landings.
In the early 70s, the Soviets sent a rover to the moon called Lunokhod 2, and that thing went 39.1 kilometers across the lunar surface, driven by some poor guy looking at a television screen and driving this thing. And it's an amazing record that has stood until about a month from now. Opportunity. The problem is we have to use the same unit of measure that they did, so that it's a fair comparison. But we figure that within the next month, Opportunity will pass 39.1 kilometers on the surface of Mars. So it just shows you, one, what an amazing accomplishment that was made back in the early 70s, and 2, that we're now talking about being now on Mars. A little statement about how the technology has advanced in the last 4 years. So that said, I think we're approaching a very interesting milestone, the longest distance driven on another planet.
And one thing Dave didn't mention about Opportunity is, that was a rover that landed 10 years ago now, almost. I mean, this thing it was designed for a, how many?
3 months.
3-month lifetime, and the thing has lasted 10 years. So that's a real credit to the engineering team.
Yeah, and to the winds on Mars, we figured what would kill the mission is that it would get so dusty the solar panels would stop getting energy. But we just had another dust cleaning event 2 weeks ago, and we're now up to 85% of the full power of these panels because the wind keeps putting them off. So on we go.
I wanted the delay in communication between Curiosity and Earth.
That's a good question.
Okay, so here's the sun, here's the Earth, and if Mars is on the same side, then it's 8 minutes. If the sun is here, Earth's here, and Mars is on the other side, 23 minutes. So it really matters which is too hard. But yeah, the key point is you can't have that kind of a delay in communication and not do it by robotic, autonomy. So this has been a major driver of development in autonomous systems. The rover basically thinks its way through the day's work we tell it what to do. Goes and does its thing for 7 hours and then reports back. And so we're getting a lot of development in that area of technology. But that's really the only way to explore Mars when you have that kind of a lag in your delay time. So we send up the commands, and 8 hours later it sends back the results. We do that day after day. In the meantime, it's on its own.
Where do you actually communicate with?
There is a system called the Deep Space Network. There's a station in Goldstone in Southern California, there's one in Spain, and there's also one in Western Australia. So the point is, as the Earth rotates, there's always one of these radio dishes that's pointing at Mars. And so every day, they hand off as to who's going to be communicating with the rover. So that any time of day we want, we can send up the command or receive stuff back from Mars. So it's the Deep Space Network, and it's serviced all kinds of space missions since the dawn of space.
Will they always be on that same time? Or they gotten shorter?
No, it's pretty much as long as Earth and Mars orbit, just the way they orbit, it's going to be those kinds of times. Yeah, so.
You're limited by the speed of light, which is.
Yeah, it's the speed of light, but it takes light that long to get from Earth to Mars. So.
Have any of the student interns shown interest in working with NASA later on after college?
Well, let's ask the student interns. So the question was, have any of the student interns shown interest in working with NASA? And honestly, I can say, I think so. I think some of them maybe indicated that, but I don't know. What do you guys think?
There's a lot of branches at NASA that like easily each of us can do.
I'll mention one thing that I'm trying to do. I'm submitting 2 grant proposals right now. In each grant proposal, you have to have an educational component. So I'm trying to seek funding for an intern program that would sort of extend this experience. So say that you go on to college and you spend 1 or 2 years in college, then I would have funding to bring it back in the summer to spend the summer at Ames, potentially from this experiment. So it's a continued period of mentoring. So hopefully those get funded.
That's great.
That was kind of my question. Were you in jeopardy of not being funded this year at one point?
Well, we're up for renewal.
You're up for renewal?
Yeah.
Because if you needed support, where would parents write a letter? Or how would they help?
That's a good question.
Well, we're up for new funding, but it has to be, it's a competitive process. You know, if you want your science to be good, you force your scientists to compete with each other. And this is what we mean by being up for funding. So by definition, there has to be an uncertainty. You have to write a very good, compelling proposal to get funded. So in that sense, it's the likely lead. We have to remain competitive, and part of that is in the papers we write and the proposals we submit.
But you know, one thing that you can do though is if you're in support of science and support of what we do, is actually write your congressperson, because that matters. You know, it's important for them to hear from their constituents because it makes them more likely to support whatever science funding issues that are being battled out in Congress. So I won't say any more about the process, but that's a direct way that you can.
Did you mean our intern program or our science program in general?
Me personally?
Yeah.
The intern program.
Oh, yeah.
Well, that is useful because there was a time when they were thinking about moving that out of NASA with the National Science Foundation and Smithsonian. And I think they're decided not to do that. But that, you know, funding for NASA is a more certain thing than funding to keep certain things within NASA, such as the education program. So that is something. In fact, Congress is what saved it. The administration wanted to move it out, and Congress, congressional representatives kept it in NASA.
I see a hand over here.
Yeah.
The Spirit and Opportunity had problems with dust on the solar panels. How does Curiosity deal with it?
Well, it's in the early part of my talk. We actually have a nuclear power source on Curiosity. So it generates its own power. So it's got a nuclear reactor. If you ever see pictures of it, it's the reactor sticking out there. Both out there to keep it cool, but also to keep it away from irradiating the cameras, which are way at the front of the rover. But it's got a power. The power source isn't so strong where you can drive the rover off it directly. It turbocharges a big battery, and when we actually use the rover for things, we pull from the battery. But of course, the reactor runs 24/7. It's constantly turbocharging the battery, and so we won't have this problem with solar panels and dust as we did with the other little rovers. Yeah, you had a question. We'll go over there.
I'm interested in a student perspective on how this intern program is helping NASA search for life on Mars. What's your perspective on that?
Directed at the students.
So does anyone from the intern group want to answer that question about how your research helps us search for life on Mars? Maybe Adrian?
Oh yeah, because I talked to that earlier. Yeah. In my talk, day 2, we talked about like why Lassen and how it connects to astrobiology, and since astrobiology is the search for like the distribution of life in the universe and past, present, and future, by studying like environments that are here on Earth that could be similar to those that were on ancient Mars, we can then analyze what we would need, like what we would need to look for to land a rover on Mars. Like he was saying, like Rusev Crater, they looked for the volcanism, the past evidence of water, those kinds of things. That's what give you indicators in like the silica deposits. things like that. In our research last year, we had the XRD patterns, which I won't go into that, but it showed evidence of silica. That was part of our results, and so that's an indicator for life, which is found in receptors. So, yeah.
So your research sort of contributes to a database that we have that helps us interpret the results that we're getting back from the workers. Yes.
So it seems like a lot of the research is developed around water, right? So if there was water on Mars, it's not necessarily, is that by extension life on Mars? Because water is organic. So does that necessarily create organic life? Or
No,
just the
not
ability to sustain it?
It's essential, but not totally essential. It's necessary, but not the whole story. And in the early part of my talk, I said that probably the single most challenging thing about Mars is how dry it is. And that would really make it hard for life. So if you can identify that there was water, you've taken a big step. But then the flower diagram that the student showed indicates, it's not just the water, you gotta have the other things. But frankly, some of the other things are easier than the water. The energy, if you start dissolving a rock, you can do chemical reactions, get energy. Dissolving the rock gives you the ingredients, many of the ingredients, and then we've got CO2 in the atmosphere, so there's the carbon for life. So those things are relatively easy, but they all have to be available at the same time. Probably the environmental conditions are probably the second biggest constraint after water for Mars, and that's why focusing on temperature and pH like the students did, or salinity. If it gets too salty, life can't use the water. It's fighting with the ions, and there's just not enough water that it needs to do its chemistry. So, yeah, it's a multi-dimensional thing. It's not just water.
I saw a hand over here. Yeah, yes, ma'am?
I was wondering, how does the rover operate at night if it's solar powered?
That's a good question. How do Spirit and Opportunity operate at night if they're solar powered?
Okay. All right, so the key thing is that we not only have the solar panels, but we also have a big battery. And in fact, in a way, the battery is almost like the heart of the rover. And of course, the obvious answer to your question, the first part is that, that's what keeps the rover alive at night when there's no sunlight. Just like a plant all day makes organic material by doing photosynthesis, and then it spends all night long burning up that organic matter with oxygen, just like we do, to survive the night. Yeah, in the case of the rover, it's the solar panels charging up the battery, and then at nighttime, the battery keeps the rover alive. And by saying keeping it alive, the two most the cold temperatures are the big challenge that the rover faces. And the two parts of the rover that are most critical as far as temperature concerned are the electronics and the battery. Okay, and actually the battery is the most temperature sensitive thing of all. If that battery gets too cold, anybody who has charged cars, tried to start a car on a very cold morning knows that if the battery is too cold, it doesn't have much power. And so everything starts working against you the colder that battery gets. So the battery lives inside the belly of the rover in a very warm, place that we can muster. And that's what really is required to keep this thing alive. So basically, that's the answer. Anytime we use the rover, we're drawing current from the battery. The battery is charged whenever there's a source of power for it. And that's a very key aspect of how these spacecraft work and how they survive.
Yeah, Mr. Henry.
Yeah, I was under the impression that our atmosphere went 50 miles up.
Yeah, it's very thin.
And you mentioned 13 miles is...
So 80 to 90% of the mass of the atmosphere is in the bottom 13 miles. And as you go up, it's quite thin there. I mean, you can't breathe. We can't breathe very well on the top of Mount Everest, and that's only just a few miles up, right? By the time you get up past that 13 miles, it's very thin atmosphere, and you can say you still have the atmosphere. You can say you still have an atmosphere quite ways up, but you're way down in pressure. And the bottom line is that everything above 13 miles is 10% or maybe around 10-15% of all the mass that's there. So it's called scale height. The height you go where you drop the pressure by factor 2 and then 2. So it goes way up, but most of the mass is down here. And that's why you have all your weather down here, the troposphere, clouds and convection and all that energy. It's all focused in the lower part of the atmosphere where we have enough density where you can heat it up and cause convection, winds, and all that kind of stuff. Once you get above that in the stratosphere, it's much thinner.
And then the second part of that would be the water that we have on Earth is the same water that's been here.
Yeah.
Correct.
Well, you know, something I didn't get into is that we have volcanic activity bringing the water out from the mantle. We also have places like along the west coast of California where the seafloor is going down back into the mantle again, and it's taking water down with it. So there's a little bit of an exchange of water between the deep interior of the Earth and the surface. But to the best of our knowledge, the volumes of the oceans have been remarkably constant over time. So whatever is controlling this balance of water coming out, water going in, it hasn't dramatically altered the volume of the oceans over time. Actually, you're addressing one mystery. We really don't know the answer. Why do we have this much water on the Earth? You know, why should it be this much? Why couldn't it be more? Why couldn't it be less? This is part of what we're trying to explore by looking at these other planets.
When the rover's lifespan is starting to expire, does it send something to you saying that, or you just suddenly go, yeah, he's not talking to us anymore?
Second answer. Yeah, in fact, you know, you develop sort of a love affair with these rovers, you know, and then you're going along and doing all this wonderful stuff. It's almost like its own personality. And early on in this mission, you know, when the rovers were only on the surface for a few months, you know, Steve Squires, who's really the godfather, the principal investigator, says, you know, guys, every month that goes by, it gets more interesting. One day, you're not going to hear from them. Just prepare yourself for that. And frankly, it's like having two pets, you know, two dogs or two cats. If you lose one, it's not so bad because you got the other one. Oh, we lost one, it's not so bad. But there is a psychology. When it goes, it's probably going to go like that. Yeah.
If the water and volume of the Earth is somewhat constant, where did all the water on Mars go?
Good question. We think we have a pretty good answer to that, and the answer is not that it got lost to space, actually. I sort of alluded to it in my talk when I said that the crust of Mars is very rigid. Okay, the important part of having a rigid crust is that it's fractures. And if you have fractures, anybody who lives in limestone country, you know, water can get down into them and fill them up. Mars' crust has cooled over time, and the brittle part has gotten so thick that the fracture space that's down there could easily accommodate the equivalent of 500 meters of water level. We think there was at least an equivalent of 500 meters of water all the way around Mars at some point in the past. The cooling of that crust and the opening up of all that fracture space could easily accommodate that. So we think most of it pretty much went down, which is why in that one diagram I say, well, maybe down there someplace, you know, there's something cool, but we don't know that yet. But that's where most of it went. And it's just a consequence, again, of the crust thickening, the evolution of the planet over time. Yeah.
Does Mars have any surface water, even if it's frozen? Is that like ice cap?
At the ice caps, yep. You can see evidence of water there. It amounts to just a tiny fraction of what must have been there at one time. But Mars does an interesting trick. The Earth has a very stable spin axis. That's why we have the seasons the way they are. But on Mars, it's so close to Jupiter, and it doesn't have a moon like we do. Every once in a while, that spin axis